just start the recording here. So just as a reminder, this Thursday evening to Friday, we're going to do our third exam for the class. Obviously, it'll be take home and open book. You can expect 4 problems. And that will be available Thursday evening. And I'll expect that you can work on it through Friday. We will not have a lecture on Friday. So that time will just be to work on the exam. There will be homework from Wednesday's class. However, it'll be due on Monday. So there's that. And regarding the lab for this week, there will be one. I'm going to post it this afternoon, but it'll be a kind of a fairly quick one. And mostly, a lot of it's going to be a review of capacitors anyway, so it'll be good to work through it. The homework from today's lecture is fairly short. Today, we're not going to be doing much mathematical stuff, so all the problems are kind of conceptual based. And you should be able to work through the homework really quickly today. At least I estimate you should be able to. So I would suggest after today's class, immediately if you're able to go do the problems, and then this afternoon the lab will be posted, which will be fairly quick. So are there any questions about any of that? So the lab, there's a lab last week that was an online simulation. That is due at the end of the day today. There is another lab I'm going to be posting today with another simulation that's somewhat quicker. So there'll be another lab posted today. It will be due a week from today. I suggest you do it earlier rather than later though. It's again going to be fairly quick. Really, if you have time today, you should be able to do both the homework and the lab all in one day. This lab is shorter, less points, and mainly doing it as a review of some of the properties of capacitors before the exam. So yes, that's another good point. The lab from last week is due today. You can submit your work on Canvas if you haven't already. There should be a submission. Oh, okay, so Canvas says it's due tomorrow. Trust the all-knowing Canvas, I guess is due tomorrow. It was due a week from the day I assigned it, which is Tuesday. So the lab is technically due, lab from last week is due tomorrow. The lab for this week, which will be posted today, will be due next Monday. But try to do it earlier rather than later. Good. So any other questions about that? Okay, so just to review, lab from last week is due tomorrow. Lab from this week will be due a week from today. There's a homework assignment today. It's very quick. And then we will have no lecture on Friday. By that time, I expect you to use it to work on the 4 exam problems, which you'll be writing out by hand and then submitting a photo on Canvas. So I can grade your work. Those instructions will be given to you with the exam, though. Okay, other questions? All right, then let's get started with our material for today. So for the next 3 to 4 lectures, probably 3, we're going to be talking about a new type of force, which you guys have probably heard about at some point, beyond our contact forces, gravity, and electricity, static electricity. We also have things called magnetic forces. So we want to figure out what these are, where they come from, and how we compute, force strength, accelerations, field strengths for the forces, just like we did with our electric forces, our gravitational forces. Magnetic forces are notoriously complicated in that they're hard to visualize. So we're going to do our best here with the online nature of the class to try to do our best. I'm going to try to do my best to teach you how to visualize these things, but it is going to be a bit harder, the fact that we're online, but we'll make it work. So what is a magnetic force? How do we know about this? Where does this idea come from? So we're covering chapters 24.1 to 24.3 today. So from your previous science experience, probably before college, you probably talked at some point about how there are these things called magnets. They experience attractive and repulsive forces from other magnets. And like electric charges, there are kind of two types of things in magnets that experience forces, and we call those poles. So instead of plus or minus, magnets can have north and south poles. Like poles repel, like shown here. So if you have two north poles near each other, they'll push each other away. If you have two south poles near each other, they'll push each other away. So it's a lot like electric attraction and repulsion between charges, with the one exception that magnetic poles always come in pairs. So you could have a standalone electric negative charge or a standalone positive charge. We could call those ions. So you can separate positive and negative charges. However, with magnets, you can't separate a north and a south pole. If you take a bar magnet, like one you might have played with as a kid if you were a nerd like me, and you cut it in half, it just becomes two smaller bar magnets with a north and a south pole. So this is kind of in some sense it's cool, but it also makes magnetic forces a bit weirder, more esoteric, and a little more complicated. Poles always come in pairs. That's the one kind of difference here. Otherwise, the properties of attraction and repulsion, like poles repel, opposite poles attract. That part you probably knew from previous science classes. Like this part you may not have known, and it's a really kind of a neat and cool property of magnets. There's no such thing as in physics, what we say is there's no such thing as a magnetic monopole. You can't just have a north pole by itself or a south pole by itself. So how do we know about magnetism? Well, what we know just from some other classes is that iron is a material that experiences this magnetic force. So iron can be what we call magnetized. So in the presence of another magnetic object, iron can form north and south poles and then experience this attractive and repulsive force. This is a picture here of some iron filings on a table. And underneath the table, there is a horseshoe magnet. You probably know what those things look like, shaped like a horseshoe, south pole on one end of the horseshoe, north pole on the other. And the iron filings kind of line up to be attracted to those poles. So a little like animation of this idea. This is if we're looking at iron filings on a table, and underneath the table we have a horseshoe magnet and we rotate it around. You see the iron filings rotate around along with it. So they experience this attraction to the poles of the magnet, and they become magnetized themselves and become magnets. So really where we know this phenomenon of magnetism from is from our studies of iron. So basically, what we know about magnetism is that it has something to do with the electronic structure of iron. And as we'll see, it has to do with with the unpaired d shell electrons in the iron atom. But we'll get back to that. One thing I want to point out here with these images is, if you notice, the iron filings in the presence of the magnet seem to line up along these well-defined patterns. So you can see the iron filings seem to make lines that kind of curve outward and go from one pole to the other. And the lines become closer together if we're in between the two poles or if we're closer to them. So this is kind of a way, when iron filings allow us to do something we couldn't do with electric forces. These iron filings act like essentially what we would call little compass needles. And what they are doing, as we'll see in a second, is that they are lining up with what we are going to call the magnetic field, the thing that causes the magnetic force. Like our electric field in space causes an electric force, there's going to be a magnetic field that causes a magnetic force, and we could use some iron filings or shavings to actually see this field. So that has, in one way, that it's easier to visualize magnetic fields because of this little experiment you can do. So the other way we know about magnetism is that the Earth experiences and creates magnetic fields and forces. So as we know, you might know, a compass is made of a magnetic material where the needle in the compass has a north and south pole. And the north pole of a compass needle is always attracted to the geographic north pole of the Earth. And this is because the Earth is generally acting like a giant magnet, and we'll talk about why, later this week. But generally, this means that the Earth creates a magnetic field, and those compass needles like to line up with that magnetic field. So here in this picture, the white part of the arrow is the north pole of our compass magnet, and since those are attracted to the north pole of the Earth, the geographic north pole, what that means is that the Earth's magnet, and this is another thing that makes kind of magnetism confusing, the geographic north pole of the Earth, since it attracts the north pole of a magnet, must be a magnetic south pole. So it's kind of a tricky kind of thing. Two north poles should repel each other. So if our compass needle north pole is attracted to the top of the planet, then the top of the planet must be a magnetic south pole. It leads to a whole lot of naming and terminology confusion in magnetism. This is why we make a distinction between the geographic north pole, so the top of the Earth, and the magnetic pole of the Earth, which is actually a south pole. The north pole of Earth's magnet is actually down in Antarctica. So hopefully this makes sense based on the way magnets should attract and repel. If we could throw a lot of little pieces of iron out into space and watch how they would align, they would kind of align along these lines that look like this, where the lines point from the north pole of Earth's magnet, and then they loop around and they finish on the south pole. So though we can't do that, we could still kind of maybe take our compass needle at different points around the Earth and see the direction it would point. And if we did this experiment, we would see it would point along these lines. And these lines are what we're going to call the magnetic field. And over the next few days, the next few lectures, we're going to talk about the properties of these magnetic field lines and the forces they create and how we can compute and measure these magnetic fields and then compute the forces that they produce. So, but the key thing I want to point out here from a geology or geoscience standpoint is that the top of the planet Earth is actually a magnetic south pole. So something you might not have thought about, but it must be. Two north poles repel, and the top of the Earth must be a magnetic south pole, even though we call it the quote-unquote North Pole. So here's a little kind of magnetic field demo. So you can see here these things on this plastic container are compass needles that are magnetized. And then there's a bar magnet that we put inside. And as you can see, they're all like oriented randomly, but they're clearly attracted to the field created by this magnet. We see if we put the magnet in the center, those compass needles all line up along these lines pointing from South Pole to North Pole. And we're basically going to use this as our definition of the magnetic field in this class. So if we had this kind of whole array of compass needles that we could move around in space, in the presence of magnetic field, they will line up with the field. And the direction of the field is the way the north poles of those magnets point. Hopefully you can see it's random, and then when we put this inside, they all kind of line up, forming the pattern of the field of the magnet. Last time, so everyone get a chance to see it. So just like a little like drawing here is if we wanted to draw a magnetic field in space from a bar magnet, what we'd really have to do is we'd have to have a lot of these tiny little compass needles and put them around the magnet and see which way the North Pole points. Here in this drawing, the South Pole is the white side of the magnets. The North Pole is the red side. So compass needles have the same standard. The red side is the North Pole of the magnetic needle. So what we'd have to do is place a lot of these magnets around a lot of these compasses around our big magnet and see which way the North Pole of those compass needles point. So we'll see in general that the North Poles point along these curving lines, and eventually they curve to point towards the South Pole of the big magnet. By doing so, we could use these compass needles to then get an idea of what our magnetic field looks like. So we could try to connect all these little compass needle vectors. If the magnetic force, or if the compass feels a stronger attraction, we make the little vectors for the compass longer. So kind of the same standard we'd use for electric fields. And then we could connect all these vectors as lines with arrows pointing taking into account these directions. So doing so looks like this. When we zoom out a bit, we had a lot of compasses. What we'd see is patterns like this. So we connect the vectors to make lines, and we leave little arrows on to show the directions of the overall kind of ballpark direction of the vectors. And what we see is that as we get, these lines follow the same standards as electric field lines. The closer they are together, the stronger the electric field, and thus the stronger the magnetic field, and thus the stronger the magnetic force a magnetic object like a compass needle will experience. The further spaced apart the lines are, the weaker the magnetic field becomes. So you'll see a lot of drawings like this over the next kind of few days. I just want you to kind of know what you're looking at. These lines are showing you the direction, essentially, a compass needle will point in the presence of this magnet. Are there any questions at this point? So in summary, what a magnetic field line like these are showing you is the direction a compass needle will point due to the influence of this magnet. Assuming, of course, we're going to ignore the effect of the Earth's magnetic force on the compass. Okay, so some other properties of the magnetic field lines from magnets. So if there's two things that are attracting, so like a north pole and a south pole, north pole from one magnet, south pole from another, the field lines will always point from north pole to a south pole. So for instance, here you could see if we had two magnets near each other, we would have these magnetic field lines that connect from the north pole to the south pole on one magnet, but also the north pole to the south pole on the other magnet. So you can see these lines here would tell us that a compass needle placed right in the center would want to point, the north pole would want to point away from this north pole and towards this south pole due to the kind of attractive nature of magnetism. What this also means is that if we put two north poles together, oh, I'm sorry. So here's an actual drawing of, so an actual experiment of this situation with iron filings. So if we had the uh, south pole and then the north pole and another magnet, south pole and north pole, and we threw a lot of iron filings on the table, they would line up with these field lines, and you could kind of see this pattern forming. And we could do the same experiment with two like poles near each other, so like two north poles, for instance. And what we will see is that the magnetic field lines actually seem to repel each other in this case. So as you push these two north poles closer and closer together, they repel each other. And what that does to these field lines is it kind of pushes them apart. So it kind of, all the magnetic field lines coming here are kind of pushed outward, and they bend to connect to the nearest south pole. So for here, this line, it'll be this pole. For this line, it'll be to this pole. And you could see this happen with iron filings as well. Put the two north poles together, the iron filings follow lines that basically mimic these guys. So another interesting property of magnetic fields is that unlike electric fields kind of start and end on charges. So they could, like an electric field line might start at a positive charge and point away, and then eventually point towards a negative charge. With magnetic fields, they actually don't have beginnings and endpoints because the magnetic field exists inside the material of the magnet itself. Though we can't really test this experimentally, especially since we're all stuck at home, the magnetic field lines form complete closed curves. So if you kind of were able to trace these same magnetic field lines through the bar magnet, you'll see they do something like this. So a line that kind of starts here at the North Pole will curve around to the South Pole and then eventually connect back to the North Pole like this. So that's kind of this is actually a consequence of the fact that the North and South poles need to appear in pairs. You can't separate a North and a South pole because of this property. It's the fact that these two things are kind of saying the same thing. The fact that North and South poles must appear in pairs and that the magnetic field lines form closed loops, they're kind of saying the same thing. So if you wanted to like take a example of like a refrigerator magnet, one of these refrigerator magnets actually has a magnetic structure that looks like this. It's a North Pole and South poles in strips like this. And depending on how your magnet's cut, you'll have kind of equal numbers of North and South poles. And really, they're kind of arranged in this U-shaped pattern. And the magnetic field lines will kind of go from North to South Pole, but then kind of curve around inside the magnet to form a closed loop. And if you could actually kind of test this structure of a refrigerator magnet if you wanted to. If you have two refrigerator magnets, you could take them and put their magnetic sides touching, and they'll like line up and then attract each other. But if you try to slide them along each other, for instance, kind of like if you so if you attach like another refrigerator magnet here and you slide the magnet's kind of like you're rubbing your hands to like make them warm. If you slide them laterally like that, you'll feel the magnets start to repel when you line up the two north poles and two south poles. And then if you push it a little bit further, they'll attract and stick together strongly when you have north poles aligned with south poles. So it's a neat little quick experiment you could do if you have a lot of refrigerator magnets. And then you could kind of see that the north and south poles kind of come in strips like this. So what we want to do, this is kind of like the properties of magnetic fields, what they look like. But what I really want to talk about today scientifically is why these magnetic fields exist. So we're going to talk about today what creates them. And then on Wednesday, we'll talk about how we compute their strength. And then on Monday, we'll talk about how we use the magnetic field to compute the force between two magnetic things. So we're going to kind of take this in steps. So right now, we're just going to talk about the field, how we create it, and how we determine its direction. And then later on, we'll figure out how do we get the force from that field. So any questions up until this point? Okay, so the experimental fact I'm just going to kind of give to you here is that magnetic fields and things that feel a magnetic force, this is all due to the fact that there is electric current. So really it's moving charges that create magnetic fields and thus moving charges that feel magnetic forces. And we're going to talk about how this relates to like the standard magnetic material like iron in a second. But for right now, just to kind of convince you that electric currents do indeed create magnetic fields, I have these two images here. So this is like kind of a piece of white paper covered with iron filings. And in two cases, you see there's a wire that's kind of cut and moving through the page. This wire moves in a loop through the page, and this wire just comes kind of straight through the page. In both cases, they're carrying currents, and you can see that once the wires have currents that are have currents flowing through them, the iron filings align along magnetic field lines. So this is kind of a simple experiment you can do to show that an electrical current, at the very least, moving electrical charges create a magnetic field. So here you might see, if you wanted to use these iron filings to draw the magnetic field from them, here you would have a diagram like this. In fact, there's a loop of current. The field diagram looks very similar to a bar magnet, actually. As for the direction, we'll talk about how we figure that out in a second. But the actual just shape of the lines and the curves, you can kind of see here to draw them from the iron filings. Here for this straight wire, the iron filings line up around circles around the straight wire. So our magnetic field direction here would look something like this. So the shape of the current, the path that the current moves in, will change the magnetic field shape and direction. And so the thing is kind of a really neat and important connection to realize that a loop of current, or like a spinning electric current, an electric current moving in a circle, makes an electric field pattern that looks almost exactly like a bar magnet. That's not a coincidence. And the reason it's not a coincidence is because you might have learned in your chemistry classes that the magnetic fields from permanent magnets are actually due, in a sense, to a spinning current, and it's due to the intrinsic spin of an electron. So, as you might remember from chemistry, electrons have can spin. Electrons have a property called spin. So they're classically, you could think about them as spinning around their axis, but the reality of the nature of an electron spin is much more complicated than that, though we won't get into it here. And electrons have two spin states, which in chemistry and quantum physics are called either up or down. But basically, this spinning electron forms, from a classical physics perspective, as we're talking about it, a loop of current. We have a charge moving in a circle. So the electrons inside of material basically act like bar magnets. And going back to intro chemistry, you might remember from how you build up electron diagrams for atoms, that electrons pair up in energy levels, one having spin up, one having spin down. And in most materials, this magnetic effect, the two magnetic fields end up canceling each other out. However, if you have a material that has some unpaired electrons, and usually it's something where we have an unpaired electron in the D shell, what we can effectively have is that each electron acts like each unpaired electron acts like a bar magnet. And in like a material that is not magnetized, like an iron bar that isn't magnetized, these little electron bar magnets can point kind of in random directions. But if we're somehow able to apply a strong externally applied magnetic field, somehow and if we could align all of these little electron bar magnets, then we could create a whole big macroscopic bar magnet. So all of these little electron bar magnets, electron loops of current, add up into one big magnetic material. And this would be kind of how you create one of these bar magnets. So even in like a magnetic material like iron, the source of the magnetic field is still, in a sense, a moving charge. And it has to do with the fact that the electron has this spin. So it's effectively, in some ways, all magnetic fields, whether from a magnetic material like iron or a magnetic fields from a current moving in a wire, all magnetic fields are somehow caused by an electric current. So this is kind of the fundamental property of magnetic fields I want you to take away today. They are created by electric currents, and things that feel a magnetic force do so because on some level there's a magnetic current in that material. It might be a magnetic current that you're pushing through a wire with a voltage. It might be a magnetic current or an electric current caused by the spinning electrons in your material. So kind of, if you wanted to zoom in on a piece of iron here that is not magnetized, it would look like this. You have these electron bar magnets pointing up, these pointing to the left, these pointing down to the right. And if you apply that external magnetic field, you would align them all along one direction. So they act like little, in a sense, these spinning loops of current act like bar magnets or compass needles. They'll align with any external field. Of course, this is a very, very like literally cartoonish picture of what we would call ferromagnetism, the magnetism of iron. It ends up being much, much more complicated than this. If you wanted to analyze it quantitatively, figure out how much external magnetic field you need to get to align all the electrons is a very hard problem that's kind of beyond the scope of the course. But the thing I want you to take away from this is that magnetic fields are caused by electric currents, whether currents in a wire or currents due to the fundamental spin of the electron. So for our problems today, our goal is going to be to determine the direction of a magnetic field given by a current in a wire. And as you'll see here, it's very much a rule of thumb. You literally use your thumb to do this. So this thing in physics is called the right-hand rule. And bear with me here, because this is kind of confusing to teach even if you're everyone's in a room together. I'm going to try to do my best here with this diagram. So let's say we have a wire of current, right? And this wire here is this kind of like copper colored thing, a cylinder moving through the page. The current, the conventional current now is moving upward. So there's a current I in this wire moving up along the page. This current's going to create a magnetic field that, as we saw on the last page, will kind of circle around the wire. And if we threw some compass needles down here, we'll see that the north poles want to point kind of going counterclockwise. So the way we kind of relate this rule, if we want to figure out, given the direction of a current, how the magnetic field points, we use this thing called the right-hand rule. So the 3 steps of it are written here on the page. You might want to, we're going to have some problems coming up in a bit about the right-hand rule, and your homework's going to be mostly about the right-hand rule here, so you might want to write these down. So first step, take your right hand, and it has to be your right hand, otherwise your left hand will give you the wrong result. So take your right hand and put your thumb in the direction of the current. So that's shown here with the hand, right? And then you kind of wrap your fingers to kind of make a circle around the wire. So the directions that your fingers are curling gives you the direction of the magnetic field. So here, thumb points in the direction of the current, and fingers are curling counterclockwise around the wire. So the direction of the magnetic field, we know from our experiment with iron filings, it forms the shape of a circle. But the direction, how the north poles of the magnets will point, will be counterclockwise. So our compass needles, the north poles will point in the counterclockwise direction. There are, of course, more mathematically sophisticated ways to find the direction of a magnetic field, but they are also beyond the scope of this course. So we're going to be kind of using the right-hand rule here. So this kind of, it makes more sense with practice. So the best thing we could do is kind of work on some problems and look at some examples. So does anyone not have these 3 things copied down before I move on? Please send me a message to stop me from changing the slide if you're still copying these rules down. Okay, well, no messages from anybody, so I'll move on. We'll show you some examples and then we'll do a few problems. Before we get there, though, I just want to point out just some of the notation the book uses that I will use as well. That with magnetic field diagrams, as you can see, they're fundamentally 3D diagrams. You have a current moving up, and then the magnetic field circles around that current. There's really magnetic fields are by nature 3D. So we have to kind of learn how to draw some 3D vector diagrams easily. And if you're not an artist like me, Well, I'm also not an artist. If, like me, you are not an artist, drawing in perspective, 3D perspective can be difficult. So what we're going to do here is use this convention. If we have a vector, so like the magnetic field lines, they're always going to be blue, and they're vectors. So if they point, we might end up into a situation where they point into the page or out of the page. And we're going to represent that like so. So vectors into the page are going to be represented by this X. So these X's would mean a magnetic field line that's pointing in the direction into the computer screen. These blue dots down here represent a magnetic field that's pointing out towards us, towards our face. And we could do the same thing with currents. If we have a wire here that's moving into or out of the page, so this circle here would be kind of a conducting wire. If the current is moving into the screen, we'll represent it with an X. And our book always uses purple to represent electric currents. So this is a current moving into the page. This is a current in a wire that's traveling out of the screen. And this is actually, if you are wondering, if you remember in class, I came into class a few times with this large, very large, big arrow made of 2-meter sticks with a cardboard arrow at the end. That was originally supposed to be my 3D vector that I could use to point out of the board and into the board. That's why I had that thing. Alas, now I am not able to use it for class. But hopefully this is hopefully this makes sense to everyone, this convention. So, all right, so here, let's take an example and look, for instance, at a current that's moving in this loop of wire. Obviously there would need to be a battery or something connected somewhere in the wire, but we haven't drawn that, so let's just not worry about how the current's created, but we have current in this wire moving in a circle. Battery not shown. So different ways we could draw this. So if we look at it from the side, the current here is moving counterclockwise as we look at it from this direction. If we wanted to look at it from a perspective view, it would look like this. So if we want to connect this thing to the convention we defined on the last slide, what that would mean is that we would be looking straight on at this green plane. And then the points where the wire loop hits the green plane, that's going to be, we could draw the current coming out of the page here, out of the screen, as a dot. So this current coming out of the green plane is this dot. This current, as the current loops around counterclockwise and goes into the plane, then we would draw that as a vector with an X, the current vector X going into the plane. Obviously, if we looked at the other side from the other side, things would be reversed. So it really depends on how you're looking at it. But hopefully this helps kind of see the convention. So all of these 3 diagrams are representing the same thing. So as an example here, using this current loop, we can use the right-hand rule to determine the direction. So this is kind of an example of how to use the right-hand rule. So we take that current loop from the last slide with current coming out of the page up here at the top, current going into the page or screen down here at the bottom. So what we can do to find the direction of the magnetic field. So here, and I encourage you to try to practice this along with me. This requires some wrist contortions to do the right-hand rule effectively. So here, to do the right-hand rule, I would take my right hand on the left of the page here and align it like the hand on the screen. So I hold up my right hand and my thumb is pointing out. So my thumb represents the current and it's pointing out towards my face, as if I was going to you know, my thumb is pointing directly at my forehead right now. So if I wanted to find the magnetic field caused by this current, I then curl my fingers, I would imagine curling my fingers around the wire, and the direction my fingers curl is the direction of that magnetic field. So my thumb points out, my fingers curl counterclockwise around this top part of the wire. So the direction of the magnetic field loops around these wires is counterclockwise. That's the direction a compass needle thrown at this point will point. They will point down over here. Compass needles will point up over here. And you could see that if you want to do the same thing down here with the right hand, my thumb would point. And this is where some wrist contortions are needed. My thumb points into the page along with the current. And then my fingers would curl, in this case, clockwise. If we wanted to look at this same right-hand rule example from the side, here now I'm showing the loop of current going around. So the current's going counterclockwise around this wire loop. Again, battery producing the current not shown. And if I wanted to do the right-hand rule, I could pick any point on the wire. I could use whatever is easier. So I could use the bottom part of the wire or the top part of the wire or some of the sides. Here, the example is shown using the top part of the wire. So I'm going to point my thumb in the direction of the current at this top part of the wire. So my thumb points kind of this way. And then I have to see how my fingers curl. So my fingers curl around the wire and then out towards my face in the center part here. That means the magnetic fields point out of the screen at this point. So we represent them with blue dots. If I had absurdly and grotesquely long fingers, I can continue looping them around the wire, out of the page, and then to go back and touch the palm of my hand up here. And we'll see at this point, as I keep curling my fingers curl into the page. That means up here, the magnetic field loops around, comes out, and then goes back into the page on the outside of the loop. So we represent the magnetic field out here with X's. So again, this is kind of hard to follow even if we're all in the same room, but I'm hoping that these figures are kind of getting across this idea of the right-hand rule. So the best thing to do here is to do some practice. So I have some problems for you guys here. And last thing, just an example from the right-hand rule, again, highlighting this fact that a current loop, a spinning loop of current, basically creates the same field as a bar magnet, kind of highlighting this fact that the magnetic field due to this bar magnet is due to the spinning loops of current caused by the electron spin. Another kind of example of the right-hand rule here, if we had kind of a coil of wire, like a spring or something, that we pushed a electric current through, the right-hand rule, to get the direction of the magnetic field, we apply the right-hand rule to each loop. And what we'll see is that the current kind of loops into and out of the page the same way in every loop. So the magnetic fields kind of just add together. This type of structure, this like spring coil with a current going through it, it's called in physics and engineering a solenoid, and it creates the magnetic field lines inside become very strong and very straight and uniform. So this is used for a lot of variety of applications, but one that's common in medicine is an MRI magnetic coil. So if you're doing MRI imaging, you need a very strong uniform magnetic field, and MRI machines have these big, loops. You put the patient inside this big loop machine. Inside that loop, there's a lot of coils of wire with high current to create a strong uniform magnetic field in the center of that loop where we put the patient. So, but just kind of another example showing kind of the right-hand rule determining the direction. So, all right, here's the first problem I have for you guys to think about today. And just checking on the time here, I know we're a little bit over, but if you need to go, feel free to leave. I won't hold it against you. Those of you that want to stay and think about, I really only have 2 or 3 problems, and they're all conceptual based about the right-hand rule today. So if you need to leave, go ahead. I know I ran over a bit, but otherwise, for those of you that are staying, try to let's look at. So here I have a current, and the wire here is coming out of the page, and we've thrown down some magnets. The north poles are the red side of the magnet. Using the right-hand rule, can you determine whether this current is going into or out of the page? Try to think about it for a bit, and if you think you have the answer, then text to the group chat A, B, C, or D. And of course, if you have any questions, feel free to ask them now. Okay, we got a few answers. Everyone so far in agreement. Give it another minute or so for other people to chime in. Okay, well, all of our answers, so far everyone is saying B, and I agree. So the answer is indeed B, it means out of the page. So we would draw that as a current here, as a dot pointing out of the page. We get this because the north poles point in the direction of our magnetic field loop. So they're rotating counterclockwise. All right, let's try one now. Let's try a different one. So here we go. This is also, of course, similar to what I was showing you before. But what's the magnetic field direction at the point here in the center of this loop? Again, it's using the right-hand rule. So here we have a few answers, 4 answers coming in. All of them are C, and those are correct. Just to show you why, like how this one's much harder to do. But let's pick the point at the top of the loop. So here I'm going to hold my right hand and my thumb is pointing out towards my face. So you could think of this black dot, or here my thumb is pointing out towards my face. That's my thumb is the red dot, pointing in the direction of the current. The fingers in my hand as I curl around the wire are going to curl like this, like I'm going to draw them. So they're going to curl in this direction until they close to make a fist. So that means right here in the center, my fingers are curling to the right. Of course, over here, if we were asked about this point, that means the magnetic field will point down right here. Over here, the magnetic field would point up. But we're asked at the point in the center of the loop. So we want to get the direction of our fingers right here. We could do the same thing down at the bottom part of the loop, but since our thumb is pointing into the page, with my right hand, if I curl my fingers, they'll curl this way. So using either part of the loop, you can get the result. Actually, it's funny, the common mistake with these problems is to use your left hand instead of your right hand, which gives you the exact opposite answer because of the mirror image anatomy of your left hand. So don't do that. Make sure you're using your right hand. That's why it's called the right hand rule. Nothing against left-handed people. It's just how it works. All right, so last one here. Here we have a solenoid loop. So a stack like a coil of loops of wire. And here, the arrows are giving you the magnetic field. So now the arrows are telling you how your fingers are curling around any one of these loops. So can we figure out from here whether the current is flowing clockwise or counterclockwise? Look, clockwise or counterclockwise is looking down from above. So like, imagine we're looking down, so our, eye is here looking down. Yep, so you guys are saying B, and I agree, it's B. Unfortunately, I didn't copy the answer slide here. So I don't have a slide that will highlight this in red, but yes, you are correct. The answer is B. So those are, it seems like you guys kind of got the basics for finding the direction from the current. There are a few problems like this now on Mastering Physics. I suggest you go and try to practice them now. But that's the last problem I have for you today. Try out the Mastering Physics problems, and don't forget to keep an eye out for the new lab that will be posted today. And thank you all. Sorry for going over, but thank you for hanging out and practicing.